Right, so let's continue with integration. So we talked about the general idea of integrals, how they are the area under the graph and how they are the opposites of integrals or inverses. And so now we will look at how to compute them, how to go about them. Right, so integration aside, let's first look at some derivatives. Let's look at the power rule. The power rule states that for any x to the n, when you differentiate it, it gives you n multiplied by x to the n minus 1. Right, so the differential of something, say, x to the 3 over 3 would be x to the 2 multiplied by 3 divided by 3. So this cancels, which is just x to the 2. And the differential of anything like x to the 4 divided by 4 similarly would be x cubed. Right. So now using the idea that differentials and integrals are inverses, if we got over here through differentiating, so if we go backwards, it will we will have to use integrals. The integral of x squared would give us x cubed divided by 3. Similarly, in the second case, when we integrate x cubed, sorry, here it was x squared. Similarly, when we integrate x cubed, we get x to the 4 divided by 4. Right, so what you'll realize is that generally for any x to the n, when you integrate it, it gives you x to the n plus 1 divided by n plus 1. Right, notice how this is the complete exact opposite of differentials. In differentials, you were first dragging the power down, then subtracting 1 from it. Over here, you are adding 1 to the power first and then dividing by that new power. Right, and oh, also here there should be a dx because we are differentiating in terms of x. All of dx is there. Right, so let's take a graph and let's say we take, let's say something like y equals 4x plus 1, and then I take another graph which is the same thing but shifted up. So it is y equals 4x plus, let's say, 3. Right, so let's differentiate both of these, 4x plus 1, and let's also differentiate 4x plus 3. Right, so this will give you 4 and this will also give you 4. Notice how these two differentials are the exact same. And it makes sense that they are the exact same because when we look at the change in x over, when you look at the change in y over change in x, that remains the same no matter how much you shift it up or down, right? You only changed this constant over here, and this constant was not linked to the x, right? So your y value is still changing the same with some change in x, right? Your gradient remained the same as you shift up and down, right? So this constant over here, it doesn't matter when you're differentiating, right? And if you differentiate this as that only their constants differ, they will give you the same answer. Right, so now let's try to integrate 4 dx, right? And so we know that it's x to the power 0, so let's add 1 to the power and divide by that power. So this would give us 4x. Now notice how it's giving us 4x, but this is neither 4x plus 1 nor is it 4x plus 3, but when we differentiate this, it also gives us 4, right? So using the idea that integrals are opposites of differentials, an integral should take us back to over here or should take us back over here. But if we are inputting just 4 and these two are different, how will we get to, how will we input the same thing but get to a different answer? Right, so over here, what you realize is that when we differentiate this thing, there's always a possibility that there's some constant added over here. It could be 1, 2, or 3, or whatever, right? If we look at the first function, here would be a 1. If you look at the second function, here would be a 3. Right, so whenever we are integrating such that we want a function, another function in return, whenever we are done integrating, we add a plus c over here. Right, so let's say the integral looks something like this, right? And if I'm adding a plus c, this means that, sorry, this means that this thing can be up or down anywhere, right? We don't know that. There's just plus some constant c. Right, so this is one thing that I have been ignoring up till now. Notice how over here I never wrote plus c, but in reality, whenever you are differentiating such that you want an integral function, you always add a plus c over here. Right. So now let's take a graph that is okay. This would be something like x minus 4. Right. Let's say this is a graph with 2 over here and 4 over here, and let's say you want to find this area. Right. So notice how integrating from up to 4 will give you this blue area, and integrating up to 2 will give you this purple area. So subtracting the blue minus the purple will give us this yellow area. Will give us this yellow area. Right, so what we want to do is we want to integrate this thing, right? And we want, okay, so let's first integrate this x squared minus 4x dx. This would turn out to be x cubed over 3 minus 2x squared, and then some, and then plus some constant c. And let's call this function sum f of x. Right, so now what we need to do is first we need to input 4 into the function because it will give us the purple area, and then we want to subtract 2 from it. Right, so let's do that. So 4 cube over 3 minus 2 times 4 squared plus some constant c which does not have an x minus 2 cube over 3, this is a cube not 23, minus 2 3 squared plus some constant c. Right. So this would turn out to be 4 cube over 3 minus 2 times 4 squared. And now notice how this c and this c cancels out. So your equation just becomes minus 2 cube over 3 plus 2 times 3 squared. And so whatever this value turns out to be, it will be this yellow area. Right, so the thing here to note was that it did not depend whatever C was because in the end it just cancels out. Right, so instead of just expanding it out every time and writing C out every time just to cancel it out, whenever we want to integrate such that we want to find the area for, we don't want to find the area function, we just want to find the area under certain graph from some point to other point. So in this case, we wanted to find the area from 4 to 2. So our upper bound was 4 and lower bound was 2. And our function was x squared minus 4x in terms of x. Right, so this is the lower bound, this is the upper bound. What we do now is, in this case, we can just simply ignore the c. So let's integrate it like we just learned to. So minus 2x squared, and then write the bounds over here. Right now, what you could do is first input 4 into this. So it would turn out to be 4 cube over 3 minus 2 4 squared, and then subtract when you input 2 into this. So minus 2 cube over 3 minus 2 2 squared. Right, and this will give you the same thing as over here. Right, this is supposed to be a 2. Right. So instead of having to write C again, whenever we have two bounds, we can simply use it like this. An example of this would be that suppose there's a car, right? And from t equals 1 to t equals 3, let's say it covers a distance of let's say 2 meters, right? And you're plotting a displacement time graph. So, and displacement from this point x, right? So it doesn't matter what the initial displacement was, it doesn't matter where the car is at t equals 1, because as long as its velocity remains the same at from t equals 1 to t equals 2, it will still cover the same distance, right? It will still cover 2 meters. Right. So if my car's velocity from time equals 1 to time equals 3 is constant, it will still cover the same distance. It does not matter what its starting point was. On a graph, what it would look like, let's say the displacement time graph is something like this, right? So at 2, there's some displacement, and at sorry, at 1, there's some displacement x, some displacement y, and at 3, there's some displacement y plus 2, right? So if I just simply drag this constant up by some value, some constant c. Let's keep one over here. Okay, let me make a new one. So let's just say this, and if I just shift this up by some value, the difference between the values from 1 to 3 would still be the same, right? And this is why you could just ignore the C also, because it just cancels out, right? You were just shifting it, but since the shift did not affect how much y changes with x, that's why this difference remains the same, right? One was giving you, by inputting one into this integral function, gave you the displacement at one, and inputting three gave you the displacement at three, and the difference between them remained the same, right? So let's take a look at another example. Let's say there's some function minus 2x plus 4. So it looks something like this. And let's say we integrate this, so minus 2x plus 4, and we integrate this from, let's say, 0 to 4, right? So minus 2x squared divided by 2 plus 4x from 0 to 4, right? This would turn out to be 4 minus 4 squared plus 4 times 4 minus 0 plus 0, which is just 0. Right, so this would turn out to be minus 16 plus 16, and this turns out to be 0. I noticed how we are integrating this, but it turned out to be 0. And the explanation behind it is that whenever you go below the x-axis, or when your y values are negative, this area will also be negative, right? So integration is actually the signed area, right? Whenever your y values are negative, your area will also be negative, right? So in this case, this positive area was equal to this negative area, and hence your integral turned out to be 0. Right, just looking at some other integrals and using the same idea that they're opposites of derivatives. If you have something like a to e to the power ax, we know its differential would be a multiplied by e to the power ax. Right, and so its integral would be e to the ax divided by a. Right, so let's say I have now something like 1 over x squared dx, and I want to differentiate this. So I can write this as x to the power minus 2. Well, x to the minus 2 plus 1 would be minus 1, and then divide by minus 1. This is just minus 1 over x plus c, right? So let's say now I want to integrate this from 1 to infinity, right? Just bear with me. So wait. I already know the differential. So this would be from 1 to infinity. Right, so negative 1 over infinity minus 1 over 1. This is minus 1 over infinity plus 1. So anything over infinity is 0. So this will turn out to be 0, and this is 1. Right, so there is this certain graph that when you find its area between 1 to infinity, it gives you this this value 1, which might look weird that you are finding area up to infinity, but it's giving you a finite value. So let's take a look at what x to the minus 2 or 1 over x squared looks like. It would look something like this, right? Not like that, something like this. Right, something like this. So it would be a graph that's getting, okay, let me fix this a bit. It will be a graph that's getting smaller and smaller, and as x is increasing, it's getting closer and closer to the x-axis. Although it's never touching the x-axis because 1 over 0 is just undefined. However, it's getting closer and closer, right? So we took the value 1, which would be something over here. So when we found out this area, this turned out to be 1, which makes sense a bit because here the area will keep on getting smaller and smaller and it will approach some value. That some value turned out to be 1, right? As your x is increasing, this is getting very, 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 very small. All right, so the last thing that we can briefly look at is the chain rule. So when you want to differentiate something like x plus 5 to the power 5, what you do is you take the power. Okay, let's make this 2x so it's more clear. You take the power down, subtract 1 from the power, and then multiply by the differential of the inside. Right, so taking the opposite of this, if I want to integrate this, what I will do is I will first add 1 to the power, then divide by that power, then divide by the differential of the inside, which would be 2. Right, so this would be 2x plus 5 over 6 multiplied by 2. And of course, if I differentiate this again, this would be 2x plus 6 minus 1 from the power, drag the power down, multiply by the coefficient, 6 into 2, and these cancel out, and it gives me back the same thing. Right, so I think that's it for the computation for now. We can look at volumes of in 3D for the next video. That would be for AS, not in O-level syllabus. Right, till then, bye-bye.